Welcome. As James said, I'm going to be talking about Docker from scratch. So what I found as someone who's been spending a bit of more and more time doing things with Docker is that people don't necessarily talk about how you get started with Docker. Everyone talks about how it's awesome to run these like multi-container microservice architectures in production, but unless you're spending a lot of times in the DevOps space, you probably don't even know what that means, like where to even get started. Like you install the Docker tools for Windows, great. Now what? Like what does that mean? So that's kind of the premise of this talk. Is I want to talk about it from the developer's perspective and someone who's heard of Docker, can possibly spell Docker, maybe even spell containers, and then we'll take it from there.
I in Docker, by the way.
Yeah, there is a C as well. I was seeing if people were actually awake and would pick that letter up. So, as I said, this is Docker from scratch. So, that's kind of a joke in the title of the talk, because there's a concept in Docker called Scratch, and that is the most basic way that we can work with Docker. And I'll work the direction of this talking precisely what that means when we're working with Scratch. But to get started, I have a Docker image here. I have Docker here, and I'm just going to run a lovely little PowerShell script. It's going to run a little application that I wrote in Go that outputs some stuff to the console and interact with that, and it says, yay, I did something, and awesome, I've made a command line application that reads input. Go home, guys. That's Docker. Yeah. First off, I had to learn Docker, and then on top of that, I had to learn Go, and then I had to relearn PowerShell, and then I had to be able to run that from a command line. No. So the only reason that I wrote this in Go was because I wanted the most basic application that I could run on without any external dependencies. It doesn't need the .NET CLR or the JVM or anything like that. It was just and I get to collect $200. Thank you for that. So, how did this all work? Well, I started with what's called a Docker file. If I come over to my VS Code, just close down all the other files. I have this Docker file here, which is called, which by convention, Docker looks for a file called Dockerfile, and that's where it expects a series of instructions that tell you what you're going to do with what you're creating. So this is what we use to ultimately create an image. And then images are used to create containers. And this is where some of the confusing terminology is, because people start throwing around this to you and like, I know those words are English, I can spell those words, I don't necessarily know what they mean in context of Docker. So Docker has two primary concepts. It has images and containers. An image is a representation of some kind of application state, some kind of environment potentially, or something that you can work with. And we can look at those on a machine by doing Docker images. Images. This is going to be full of live coding, so expect a lot of typos. Is the font size good enough for people down the back? Is it okay if I drop it a little bit? I just noticed we're getting some wrapping that might be annoying. Yeah, let's drop it a touch and yeah, it looked totally better. Yeah, at least now it's not wrapping across multiple lines. So, I've run this on my local machine, and you'll see that I've got a heap of different Docker images on my particular on my machine. These are all things that I have downloaded from what's called a container registry, which is kind of an incorrect use of the terminology, because you're not pulling down containers, you're pulling down images. So a really good example of where people start with is the Ubuntu image. That's where a lot of Docker demos are. So let's say I've pulled that down. You can see that here. I have two Ubuntu images on this machine, or at least two available in my image list. I'm not going to do a pull because we don't need to sit here and watch me download a bunch of stuff from the internet, but normally I would do Docker pull Ubuntu, and that will download that particular image from some kind of container registry. By default, it will look for the Docker container registry, which you'll find at store.docker.com. You can have your own custom registry. So in Azure, you've got the Azure Container Registry or ACR. AWS has a container registry, or you can stand up your own, whatever works for your organization. Okay, so I've done a Docker pull, I've got down Ubuntu, and then I do Docker run Ubuntu. Yeah, I'm going to run a container from that image. But that didn't really do anything, did it? It just kind of, a command line executed. And what I did was I actually started a container. I started a container that's running the Linux version, the Linux distribution Ubuntu. And it executed, got to the end of what I told it to execute, and then finished. So we can see that if we do Docker PS, so processes, and then I'll use the -a command to list all the running Docker containers or the stopped Docker containers.
I need to bring it up top for heads.
Yes, good point. Whoop. Okay, so running Docker PS, you'll see I have an image that was run called Ubuntu. It executed a command, bin bash, so started a shell. It happened 29 seconds ago. It exited 27 seconds ago, and it's got some IDs and names and stuff like that. Cool, I ran something, but it's now stopped, or it's exited, and I didn't do anything with it. It did nothing, right? Well, that's because I didn't give it a command to execute, so it fell back to its default, which is trying to run bash. I also didn't have any way of interacting with it, so it then terminated itself because it received all the input that it was ever able to receive and exited. So that's how we ended up there. So let's say I want to run an image, or I want to run an instance of an image as a container, but I actually want to run a particular command inside that. Let's do Docker run Ubuntu ls. So this is a breakdown of the Docker command line. Is Docker is obviously executable, you're going to execute. The command that you want to execute against Docker, in this case run, an image name that I want to use as the image that I'm running, in this case Ubuntu, and then a command and any arguments to that command go after the name of the image. So in this case, I want to execute ls. So I ran a directory listing command on something that ran and then immediately exited, because if we do ps-a, and I'll just scroll up again, you'll see that there's another one in the list, ls. It exited 10 seconds ago, because the ls command, what's it do? It lists out a directory, and then that's it done. I could, that's how you can run a container and get it to do whatever you want it to do. I could tell it to run a particular executable. In this case, an executable I know that's on disk, which is called ls. I could rerun that, docker start, and I'll just use this container ID, 37. And then if we have a look, see that it started 3 seconds ago and then immediately exited. We didn't see any output to the screen that time. It's because when we started the container, it ran it in a background mode. So I could do docker logs of 37. Because it ran ls and then we ran it a second time, you'll see bin, boot, etc., etc. If we scroll down, you'll see about middle of the screen we have bin boot, and that ends in var, and var was the last one there. So we just kind of kept appending ls to that log. So this is how you can see a container that you've started up that's done something, it's exited, and I can go back and inspect that. The container's not running anymore, so I can go back and look at what that container is doing and see what it was. And now this is where the difference between an image and a container starts becoming apparent. An image, as I said at the start, is a representation of a point in time. So it's an environment, it's a particular machine, it's an application that's going to be executed. I can create multiple containers that use that image, and they do different things. So I started with the Ubuntu image, and I've run two different commands. I ran bash in one, and I ran ls in another. It still started the same image, but I'm doing different things inside of them. But so far, these are just executed and then immediately terminated. Well, let's say I actually wanted to do something with inside of that container. I want that container running, and then I want to, it's a Unix shell. I want to be able to interact with this. So we'll do docker run again, because we're going to run our image, run our container from an image. Going to pass in a command line argument of it to specify its interactive mode. Ubuntu again, and this time I'll tell it that I want to run bin sh, because I want to run a different command this time. So my prompt has changed. Sorry, I'll just scroll that up for people at the back. Now I have a £sign there because I'm actually now inside a Unix machine. I know this.
Thank you.
Yeah, I know that there was at least one person other than Richard in the audience that was waiting for a Jurassic Park reference. Yeah. So yeah, here I am. I'm on a running Linux machine, running the Ubuntu flavor of Linux. It's got a file system that I can interact with. I can have a look inside of bin. I can have a look inside of the user. I have a home directory. I can run something like, because this is running sh, I don't really actually have very good interactive stuff. I can't use the backspace key. I can go, oh, I've done it again. I've done it a third time. Bash. Okay, so I can go into a bash shell instead of an sh shell. Sh is really basic and brutal if anyone's tried to work with it. Cool. So now I'm in bash, which is slightly better. Let's say I want to, I don't know, check to see, huh? Yeah, who am I? Cool. I'm running as the root user. So I'm logged in as a user on that machine. It's only got a single user on here, which is root. I could run commands to create multiple users if I wanted and stuff like that. But let's say I want to see is Google up? Ping. Oops. Hey, I can use the backspace character. Google.com. Oh, hang on a sec. I can't ping. Wow, wow. That's because this is a really basic install of an operating system. It doesn't have a whole bunch of software on there. It doesn't even have something as simple as ping. I don't have VI or Emacs or anything like that. I've got, huh?
Edlin?
No.
Go on.
No, because I don't know how to get out of it. So this machine really doesn't have a whole lot on there. Instead, I could do like it does have apt-get though. Get update. So I can run an update on here, download the latest information from the Ubuntu package repository. This will take a while, so I might leave that running in the background. We can see that running from my terminal. And eventually this will have done an apt-get update, and I'll be able to then install other packages like VI, for example. Okay, well, so I have a Docker container that's running on one tab in my terminal. If I want to see what's happening, I can do docker ps and go, oh, yep, there we go, it's running. The command that it used to enter was sh, bin sh. But what's it actually doing internally? I've got no idea. I don't know that it's running apt-get at the moment because this is running as like an entirely isolated little unit of work. Now, it's not a virtual machine. That's a common mistake people often make when they come to Docker is that, oh, Docker's about making virtual machines. It's not about virtual machines, but it is a form of virtualization. It's what they refer to as kernel mode virtualization. So I've created a virtual instance of the Linux kernel with a virtual file system that's all self-contained within inside of that running container. So it has its own process tree, it has its own memory management, it has its own file system, it has all of that kind of stuff. It's still subjected to the rules of the machine it's running in, obviously. It's not actually able to turn itself into a 6-processor machine if you're running on a dual core or anything like that. But it is for all intent and purpose a self-contained machine that that no one knows what it is actually doing internally. I can do logs of what's that 2a. Okay, so that's what it's doing. You can see it's doing an apt-get. That's how I can inspect what's happening, to stand it out. If I do follow, I can obviously observe that apt-get as it downloads. We don't get the live updating thingy, but we see that it's up to step 9 and so on and so forth. So that's how I can see what's happening on a container that's running on my machine. I could always start up another Docker image, sorry, the Docker container, Ubuntu bin bash instead because I want a slightly more useful shell. Now I have 2 instances of Ubuntu that they don't even know about each other. These can be running independently. They can be doing their own app. In this one, I'd have to do apt-get update as well if I want something to happen with inside of it. If I want to be able to download packages, I install software here. It's not available to any other running container or any other stopped container. Let's exit that one. So I've exited that one, and if we PSA, So was that 39 was the last one that was executed. You said it exited 2 seconds ago. So because the application that I ran when I entered that container terminated. Stop. Cool. So we're understanding the basic premise. So we're able to pull down these pre-built things that we can either have them run a single application, like something like LS, or we can interact with them, jump into them, run commands, apt get install vi. Do vi because I actually forget what you have to install to do ping install. Oh no, it's vim. Forget what ping is. It's somewhere. Yeah, cool. Okay, so
just a quick question on that. You're doing all this to this, what is now a container.
Yep.
When that container finishes, does it just go away and all that work that's just been done is lost, or does it stored somewhere?
So it's a good question. Good question. So for the recording and for people down the back that might not have heard of it, the question was, what happens when you stop that container? Is anything that happened with inside of it lost, or like what happens? Well, when you stop a container, basically it's like powering down a machine. It's still there. I can restart it. So like I did before, where I did Docker run and then reran the ls container. So I can bring that back up. It will pick up wherever it left off. In this case. It'll be a good illustration once I get VI installed, but I can, because it's the command that's executing is bash, I can then reattach to that shell session, kind of like screen, but it's been offline for a period of time. I can then come back in here and I can use VI, which I've just now installed, or will have momentarily installed. So it's still all there. That is until you remove that container. So we'll just, so wait a moment for this to install. So now I can do VI, and we can create a random password because I have to try and work out how to exit. It's a lie, I actually know how to force quit. So if I exit that, and exit SH because I forgot that that's where I was in, and then just scroll up, sorry, Docker PSA, you'll see that that one's now listed as stopped from 8 seconds ago. To A7 is the container ID. If I was to do Docker start to A7, and then I could do Docker attach to A7. I'm now back into that shell session that I had. I have which VI, so VI is still there, so I could now go back in, I could edit VI. I have the same file system, so any files I created, I still have access to on this machine. So it's all there. Now if I was to do Docker RM, so this is how I could remove a stopped container. So RM and 2A7. So I've removed that container from the machine now that it was stopped. Docker PSA, see that it's no longer listed there. I can't obviously go Docker start to A7 because it doesn't exist. I now no longer have anything that lived within inside of that machine. No, I don't have VI installed on any of my containers anymore. I don't have files that I created there. They're all gone to the ether essentially. They're removed. So I'll talk about how we solve that problem in a moment, but I want to kind of segue into how we get there. So that's all well and good about we can start Unix shells and stuff like that. Woohoo! We've got Windows 10, which has got the Windows subsystem for Linux, so I can start a Unix shell anyway. That's no longer a cool thing to do. And the other thing people tend to talk about is how I can use Docker to run a production system. But where's that intermediary? We're starting to wet our feet in using Docker. I know how to start interacting with it. I can run containers. I know what a container is and the difference between a container and an image. Well, let's see what we can actually do with it. So when I install Windows, I try and keep it as bare bones as possible. I don't like installing single-use pieces of software. I only kind of install things that I'm going to use multiple times, and even then, I will try and avoid installing things until I really desperately have to. And by and large, I can get away with this. I can pave my machine, and all I have to install is Office, Visual Studio, this terminal wrapper that I've got, and VS Code, and I'm pretty much set for all the things that I do day to day. That is until I'm doing something like, recently I was doing a Redify technical interview, and I was reviewing the code that the person had sent to me, and they'd sent it as a .7z file. That's 7-zip. This was the first time in years I'd seen someone use a .7z as an archive format. Oh no, I had a RAR file as well, but it's basically the same story. So kind of back-to-back interviews. One was a 7Z, the next one was a RAR file. I'm like, what is this? 2005, and zip is no longer a cool archiving format, so we need something a bit more obscure, and that we then need another piece of software installed. Like I said, I survive very, very well on just the Windows archive and Windows unzipping stuff that's built into Explorer. I don't need to install 7-zip to unzip a zip file, right? But I have to unzip a 7-zip file. So I'm going to do this in the most complicated way possible. I am not going to install 7-zip. First thing I do is I go into the Docker container registry. Does someone have a 7-zip container? Because 7-zip works on Linux. Someone has got to have made a container that's got 7-zip. And if I do Docker images, lo and behold, I have one here called...
From Daniel Whatmuff.
Yeah, look, I don't care who it was. I don't care who this person was that's created it. They've created an image that's got 7-zip in it, and that's what I need to solve my problem, because I've got an interview in 15 minutes, and I probably should read this guy's code.
You downloaded it 14 months ago, right?
No, so the timestamp is when that image was created and uploaded to the Docker registry. So when it was on the container registry, not when it was created on my machine. And here's another command if I want to work out when it was downloaded to my machine. I have to inspect that image, but that's fairly immaterial. It just means that there's not been a whole lot of changes to 7-zip. It might not be the bleeding edge betas version of it, but that's fine for archiving my archive. So, rather than trying to run this command from memory, I'm just going to go to my cheat sheet and grab it. So here is a command that I prepared earlier. So I'm going to use the docker run command. I'm passing in another flag, --rm. What that does is it tells this container is once you've finished, once you exited, remove yourself. It's an RM command. I have no need for this container. I'm never going to execute this command again. Just remove yourself. And then pass a -v flag, which I'll talk about what that does in a moment. It gets back to your question that you had before. A -w flag, which sets the working directory of this container when it starts up. I'm pulling down Daniel Whatmuff's 7-zip Docker. I'm then executing the 7z command, x to unarchive, and then to a archive file called archive.7z. Now, we'll execute that, and there we go. Hang on a sec, I don't actually have a file in here called archive.7z. Instead, I have that in a folder on my machine up here called TMP. And if anyone's interested, this was the contents of the zip file, the 7z file that Richard sent me earlier today. Because I don't have 7-zip, so I couldn't make an archive to then demonstrate this. And I didn't want to pull up the poor person's code during a recorded session. Sorry, Maligi, you get to be my guinea pig. So, let's go back to that command, and we'll just talk a bit about what it did. So, as we see, it just executed 7-zip with a particular file. I said that --rm means that the container is immediately removed when exited, but then I need to get a file that's on my machine, a file that's currently living in my download/tmp folder. I need that file to be on this container. But this is a Unix file system, not a Windows file system. It's actually running inside of a virtual machine on Hyper-V because I'm running Windows. I don't have, Unix isn't my operating system. So it's actually inside of a Hyper-V virtual machine. But I still need to somehow get this file up there. And this is where the concept of volumes comes into Docker. A volume is essentially a share between the host machine, so my Windows machine in this case, and the running container. So a volume is made up of two parts: the full path on the host machine, and then the path on the container that you want to execute. So that's what c:/user me downloads tmp. That's the fully qualified path on my machine, and then I'm going to put that into somewhere called /root. Let's just run this again, but we'll use our bin bash command. Oh, whoops, I forgot to make that interactive. Let's just make that interactive. So I've set I also set the working directory to /root. So if we have a look, you'll see here pwd, I'm in /root. And the contents of that is obviously an unarchived JPEG and the 7Z archive. If I was to come over here and go new text document and call it foo.text, foo.text is now available. If I did like an app, I don't know if this has VI, no it doesn't. So if I did like an apt-get install, I could then, from this machine, I could use VI to edit that, actually cat, pardon? Is nano on here? I don't think so. No.
Just echo into the
Yeah, echo, hello, alt, net, Sydney, and we'll just go into temp text.text. Okay, cool. Oops, wrong thing. There we go. So now I have a text file here, which. So I now have I have this volume that's mounted between these two machines, between Windows and Unix, and this is how I can then share files. I can copy things back and forth. But what it also gives me is persistence across container starts. So if I exit this container, then we do docker psa, you'll see that there's that one that's created. It didn't exit properly, but it's neither here nor there. Docker rm-f. So I want to force remove a container because get rid of it, just to illustrate a point. Docker ps-a. Okay, so that container is now gone, but these files still all exist. So let's say you're running an application, maybe it's an ASP.NET Core application, and you've got some logging that's just going to write some write to file system. You want to just do a rolling file log. Well, you might mount the log file from the host machine and then have, say, this running inside of an AWS cluster, and then you're using like Logstash to pull those logs and chuck them into Elk or whatever it might be. You're daisy chaining all the buzzwordy technologies that there are at the moment. So you mount that folder inside of the running host that your logs are just getting written to, and then some other process is able to pick it up because they're files that are available on your host machine, on the virtual machine inside of AWS that's running it, for example. So that's how we can persist things across containers, across terminating containers, and even share files between containers. Cool. Okay, so let's get back to kind of the thing with inside of the original the topic title, which was the from scratch. So far we've worked off of the Ubuntu image. I could have been using like Alpine, or in this case we just saw there, we're using something from someone that was running 7-zip inside of that. I also have in here images. I have no images. I have node, so I could do docker run rm it node. And then I'm in a node shell, console log hello. So I can, I don't want to install Node on my machine. I can run it from inside of a Docker container, mount file systems back and forth. I don't have to do npm installs on my primary OS. I can put that inside of an image and then delete that image when I realize that I've got 2 gig of data in just the Node modules folder. So all these things these are what we call base images. They're built on top of different Docker images. They build on top of Ubuntu or Alpine or Centrus or a whole bunch of different things, and that's what we use our Docker file for. Actually, I'll come back to Scratch in a moment. I'll talk about this Docker file. So this is one called Docker file. A Docker file is it's a DSL for describing how you're going to create an image. A Docker file will always start with a command called from, and then the base image you want to build off of. In this case, I'm creating one that's just building off of Ubuntu. I'm then running a command on that image called apt-get. I'm doing apt-get update. I'm then running another one, apt-get install a package called JQ. Silently, I don't prompt a -y flag, making directory, moving to that directory, and then running the JQ command. JQ, if you're not familiar with it, is a tool for inspecting JSON objects. It's kind of a query language over the top of JSON. So let's make an image. So Docker build. So I'm going to run a different command. I'm going to do the build command because I want to build an image. I'm going to tag this with alt-net, and then I'm going to say that it's in the current directory. So I have to specify where the Docker file lives. In this case, dot. current working directory. So kick that off, give it a moment. Speedy. Okay, sweet. So I've previously executed this, so it was actually really fast. So I'm just going to RMI, so remove a previously downloaded image, which is JQ. Docker images. Let's just make sure I killed the right one. I think I did. Yep. All right. So RMI, remove image. RM, remove container. Okay. So we'll just start that build again. And hope. Oh.
You need to get rid of altnet as well.
Yeah. Docker RMI alt net. Good catch. Okay. So I've completely deleted that image. You'll see it's deleted a bunch of other stuff. I'll talk about what those are in as we're building. So let's start up the build command again. So the first thing it's done is gone from Ubuntu. So this is my base image. It'll look into my local set of images. Do I have that downloaded already? And I do. I have Ubuntu already downloaded. So I'm not going to download that. The next thing it's doing is the apt-get update command. So it's running that here, and as we've seen previously, apt-get updates, they take a bit of time. It's going to download a whole bunch of stuff. But what it does is it's building an image that's already done that step for me, so that when so if I want to create another image, it won't have to re-execute this command. And that's why when I did the altnet altnet image previously, it was lightning fast. It just went up, done all those before. So what's happening under the hood is Docker is looking at the Docker file, picking out each of these commands I've got from run, working directory, entry point, and it creates what it calls layers. It looks at the command, it makes a SHA of that command relative to all previous commands that it's executed, and then tracks that layer. And when you then do a Docker build, it goes, okay, based off of this command and its hierarchy, are there things that do I have a layer that previously represented this state? Yes, I do. All right, I don't have to execute this command because I've already done it. I've got something I can reuse. And it basically keeps going and will only execute the steps that you haven't previously executed. So this, if you're using Docker in a complex application, or you're using multiple Docker images in containers across an application suite, you might have a whole bunch of things that are common. You're using the same, you're running all off Ubuntu or Alpine. You might be all installing the particular version of the .NET framework. You might be installing a couple of additional packages onto those machines. Now, it's not needed to execute those for every single command because they should be all the same. So it will only add the things that are unique. Only add the actual application that's going to be run. It's only going to expose particular particular ports on the networking stack. It'll only create the particular directories on the file system you require it to create. So
it probably has something like a tree-like structure behind the scene, which is like a tree.
Yeah, it is actually essentially a tree structure. They used to have a command that allowed you to visualize it. They've since removed that command, so you can't truly visualize the layers. But that's neither here nor there. As you'll see, it's going along and it's executing all those various steps. And by executing those steps, it's actually creating Docker containers from that step, executing a command inside of that container, putting that onto your local machine, and then removing that once it's completed. So you can actually tell it to not clean up after itself if you want from a debugging perspective, but we're not doing that here. So now back to Docker images, and we have our altnet thing. You'll see that it was created 29 seconds ago because I created that just now. Now if I was to do Docker run, then let's just do RM, because I'll just get it to immediately remove. We'll mount a volume, and in this case I'm going to do get location, and then I have a JSON file inside of the .vs code, and this will go into the /root directory, which I created inside of here. And I don't need to set. Pardon?
/JSON.
Oh, sorry, /JSON. Good point. JSON. Root was in the other one. Okay. I don't need to set the working directory because my container will automatically go to that working directory because my image has said this is your working directory unless specified otherwise. So I can override that with the -w command. Altnet, and then the command is going to execute is JQ. So I then just need to pass some arguments to that. So settings.json, So this will just, this one I probably should have remembered precisely how I wanted to do. Key JSON. What? JQ filter. Anyway, you get the idea. Gonna move on from trying to do that one from memory. I forgot to write that command down. The point of this step was more to illustrate how you could create your own image from the Docker file. So that's what the Docker file's responsibility is. Now let's say I just want to create a really super bare bones one. I don't need the full Ubuntu on there. I just want something that's really basic. I'm just going to execute a binary, in this case, a Go application. Well, yeah, like I said, I don't need Ubuntu, I don't need apt-get, I'm not going to install VI or anything like that. So this time, I might want to use an image, a base image called Scratch. If we go Docker images, you notice that I don't actually have an image in here called Scratch. I do have one called Scratchy. I'm just going to RMI Scratchy and Docker images. So I don't have an image called Scratch, but I can do a Docker from Scratch. And that's because Scratch is like the most basic, bare bones possible image that you could use with inside of Docker. It is literally Docker, the Docker engine itself, bootstrapping Docker. So that's like, it has nothing inside of it. It doesn't even have a shell that you can connect to interact with. It has no SH, no bash, nothing. So you can't really, you can't interact with it. You have to add a file to it and execute. And that's what I do here. So I have a thing here that will, it uses Go to create a binary application. It then creates a Docker image based off of the Docker file that I had on screen here. It then mounts the current location into the /app folder. It then moves to that working directory and executes my Go application with inside of there, and everything is amazing and it works all fantastically, and we get excited. And we've created an image that literally has a binary file inside of it, a file system, some of the most basic Unix level commands that you need that you can run with inside. So it is super lightweight. It has kind of as minimal memory footprint as you can. It has minimal disk space usage you've got. It'll have the most minimal space inside of your container registry, and it is pretty much useless. The only reason you would use Scratch as an image is if you're creating something that is super high performance, like Netflix scale performance, or you're creating something that is going to be an operating system style image. Scratch doesn't have a lot of general value in it. I've been given the time wind up, so I'll wrap it up there. But that's kind of what I wanted to talk about, is some of the basic commands with Docker. We saw that the difference between an image and a container. An image is something that represents an application state or an environment state. A container is then a running instance of that image, and we can run multiple containers from the same image. We can connect to an image, connect to a running container, interact with that. It will be a persistent thing until we remove it. If we want something persisted more long-term, we mount volumes. And volumes are something that are persisted back to the host's file system. So we can then have that volume shared across multiple running containers and in turn multiple images. They don't even have to be the same base image that we're starting with. I can then have single purpose containers that I can run, do something like run 7-zip or run an unrar command, or install one that has ping because you just don't want to use ping with inside of Windows. You only trust the Unix ping. You can run VI, or in this case, I was running the Go compiler inside of a Docker container because I didn't want to have to install Go on my machine. All that kind of stuff. We saw how we can build our own images with the Docker build command. We saw images appearing inside of our local image list. And then we finally saw what is Scratch in context of Docker and how that's not particularly useful to us longer term. That is Docker from Scratch. Thank you. Question down the back, yep.
Do you still have that JQ one open?
So do you mean the Docker file or the actual container? So I don't have it running, it'll be stopped, but I could do Docker run IT, actually, no, let's go back up to the command that I had, and If we go bin bash, and then I can come into here, and then I can. Oh, actually no, because I said that it said that the command it's running is that. Yeah, just go. Then dot. No, there's another thing that I'm missing inside of there, which, like I said, less than interesting at this point in time. Yeah, question?
Yeah, you've got this, I guess, a Linux application running on the Windows host.
Yep.
Can you run a Windows application on a Linux host?
Not quite. So the question was, can I run a Windows application on a Linux host? No, it's not quite like that. So the way Docker works on a Windows machine when you're running a Linux Docker container, it's actually a bit of a trick. So I have Hyper-V installed on this machine as well, and I have a Linux virtual machine in Hyper-V, and the Docker engine that's installed in Windows actually communicates back and forth with that Linux machine. Now, there is Docker for Windows, and in terms of Windows containers, and what that does is it allows me to do a similar concept of kernel level virtualization of the Windows kernel. It's not quite the same as Linux because of the differences in the Windows and Linux kernels, but it does allow you to do a lot of the same concepts. You get your same process tree isolation, you get your same file system isolation, you get your same destroy a machine, you lose the context of it and stuff like that, but it is not quite as close to the metal as you get with a Linux Docker container. And there's also two flavors of Docker Windows containers. You've got Docker, Windows Server Core, which is the really stripped down version of Windows Server. Nano Server is the stripped down version of Windows Server. Server Core is full Windows Server, but running in container isolation. That's about a 9 gig image. The Nano Server is about 900 meg. And it's actually progressively getting larger because every time there's a new Windows patch that comes out, then that's a new layer on top. So those containers are patched with the Windows operating system, so they keep rolling forward. So the first release of Windows containers was with Windows Server 2016. It also works on Windows 10. But to get into that's like a whole nother talk, and I don't want to take up any more of people's time.
So basically, if you're in a Windows environment, you can
Best of both worlds.
Yeah, so if you're running Windows as your primary OS, you can run Linux or Windows. If you're running Linux as your primary OS, you're going to need another machine to run a Windows container. Yeah, cool. Any other questions or break for more cold pizza? Cool. Thanks, everyone.